Hello everyone. Today we are going to analyze this beam using slope deflection method. Before analyzing, let us see the slope deflection equations. For every span, there will be two slope deflection equations. Consider a random span AB in a continuous beam. In this span, we are having two slope deflection equations. In these equations, M of AB is the fixed end moment in the point A. M of BA is the fixed end moment in the point B. Theta A and theta B are the slopes in the point A and B respectively. 6EI delta upon L square is the fixed end moment due to the sinking of the support. If in the question nothing is mentioned about sinking or settlement of the supports, we can assume that there is no settlement and sinking in the given beam. In this problem also, there is nothing mentioned about sinking or settlement of the supports, so we can assume that there is no sinking in the given beam. In this case, the fixed end moments due to sinking of the supports will be 0, so no need to consider these two values when we apply the slope deflection equations. We had a brief introduction about slope deflection equations. Now let us start analyzing this beam. In this beam, we are having two spans, span AB and span BC. In the span AB, we are having a point load acting on the center. In the span BC, we are having uniformly distributed load acting for the full span. Span AB is 10 meter long, span BC is 8 meter long. There are three supports in this beam, in the point A, in the point B, and in the point C. There are supports. All the supports are roller supports. In the slope deflection method, we have to check the number of supports in which slope can occur. Let us see the conditions. In the fixed support, there will be no slope. In the hinged support, there will be slope. And in the roller support also, there will be slope. Only in the fixed support, there will be no slope. In this beam, we are having three roller supports. In the point A, in the point B, and in the point C, we are having roller supports. So, the number of supports in which slope can occur is equal to 3. In the point A, we are having theta A, and in the point B, we are having theta B, and in the point C, we are having theta C. So, in this problem, we are having three unknowns. If we calculate these three unknowns, we can easily calculate the moments. To find out these three unknowns, we need three equilibrium equations. Let us see how to make these three equilibrium equations. Equilibrium equations can be made available at the ends of the beam and at the joints. So, in two ways we can make the equilibrium equations. First, we have to look at the joints. In the joints, the summation of the moments will be 0. Using this condition, we can make equilibrium equations. Then, we have to see the end of the beams. In the fixed end, there will be movement, so we cannot make any equilibrium equation. In the hinged end, there will be no movement, so we can make an equilibrium equation. In the roller supported end also, there will be no movement, so we can make an equilibrium equation. In the hinged and roller supported end, there will be no movement because they are simply supported ends. Using that, we can make equilibrium equations. Now, let us make the equilibrium equations. First, let us see the ends. In this beam, we are having the ends A and C. In these ends, we are having roller support. The roller supported ends are the simply supported ends. In the simply supported ends, there will be vertical reactions. but there will be no movements. You can see that in the point A and in the point C, we are only having the vertical reactions and there are no movements. Using that, we can make the first two equilibrium equations. MAB is equal to 0 and MCB is equal to 0 because in the points A and C, the moments are 0. The third equilibrium equation can be made in the joint. In this beam, we are having only one joint, that is the joint B. We already saw the summation of the moments in the joints will be 0. That means when we add MBA and MBC, it will be 0. In every joint, there will be two moments. One moment will be acting in the clockwise direction and another moment will be acting in the anti-clockwise direction. But both of them will be having the same value. For example, if MBA is 5, MBC will be minus 5. MBC is negative because it is acting in the anti-clockwise direction. When we add MBA and MBC, it will be 0. Using the concept, we can make the third equilibrium equation. MBA plus MBC is equal to 0. In this problem, we are having three unknowns. To find out three unknowns, we needed three equilibrium equations and we have formed them. Now let us make the fixed end moments. For making the fixed end moments, we have to assume every span as a separate fixed beam. First, let us make the fixed end moments in the span AB. You can see that I have assumed the span AB as a separate fixed beam. In this table, you can see some of the important fixed end moments for the different type of loadings. In the span AB, we are having point load acting on the center, so we have to select this condition. The formula for the fixed end moments are minus WL upon 8 and positive WL upon 8. In the span BC, we are having UDL acting for the full span. So we have to select this condition. The formula for the fixed end moments are minus WL square upon 12 and positive WL square upon 12. In the span AB, we are having a point load acting on the center. We just saw the fixed end moment formulas minus WL upon 8 and positive WL upon 8. M of AB is negative because it is acting in the anticlockwise direction. M of BA is positive because it is acting in the clockwise direction. Let us apply the values in the formula. W is 72, L is 10. After applying, we are getting M of AB is equal to minus 90 kilonewton meter and M of BA is equal to 90 kilonewton meter. Now let us make the fixed end moments in the span BC. In the span BC, we are having UDL acting for the full span. We already saw the formula for the fixed end moments. Minus WL square upon 12 and WL square upon 12. Let us apply the values inside the formula. W is 36 and L is 8. After applying, we are getting M of BC is equal to minus 192 kilonewton meter. M of CB is equal to 192 kilonewton meter. Now let us make the slope deflection equations. First, let us make them for the span AB. We know that in every span there will be two slope deflection equations. We already saw the formulas in the beginning. We can apply the fixed end moments we have already calculated. Also, we can apply the value of L, 10 meter, in both of the equations. In this equation, we can make the first equilibrium equation. We know that MAB is equal to 0. Instead of MAB, we can apply 0. and take this minus 90 on the right side, it will be positive. It is our first equilibrium equation. Now let us make the slope deflection equations in the span BC. We have already calculated the fixed end moments. We can apply them. The length of the span is 8 meter. We can apply in both of the equations. In this equation, let us make the second equilibrium equation. We know that MCB is equal to 0. Instead of MCB, let us apply 0. Then let us take 192 on the left side. It will become negative. It is our second equilibrium equation. Now let us make the third equilibrium equation. We already saw the third equilibrium equation, which can be made in the joint B. In the joint B, we are having two moments, MBA and MBC. The summation of these two moments will be 0. For MBA and MBC, we have already formed the slope deflection equations. Let us apply them. Then we have to add them. After adding, we are getting this. Then take this minus 102 on the right side, it will be positive. This is our third equilibrium equation. So we have made three equilibrium equations. The first one, the fourth one, and the fifth one. Now let us use the calculator and solve these three equations. If you do not know how to solve three equations in the calculator, see the description below. There is a link. You can click the link and watch the video for getting ideas how to solve three equations in the calculator. I have used the calculator and got the final answers Ea theta A, Ea theta B, and Ea theta C. Now let us calculate the final moments. For that, we have to apply these values in the slope deflection equations. For MAB and MCB, we don't have to apply the values in the slope deflection equations because we already know they are 0. So no need to apply and waste the time. When we apply the values of Ea theta A and Ea theta B in the equation number 2, we are getting MBA, which is equal to 203 kN meter. When we apply the values of Ea theta B and Ea theta C in the equation number 3, we are getting MBC, which is equal to minus 203 kN meter. In this beam, we have calculated the final moments. For MBA, we are getting a positive value. That means it is acting in the clockwise direction. For MBC, we are getting a negative value. That means it is acting in the anti-clockwise direction. Now let us calculate the reactions. First, let us take the span AB and calculate the reactions. In the span AB, we are having a moment MBA which is acting in the clockwise direction. So when we calculate the reactions in the span AB, we have to take the moment MBA. In this span, first I am going to calculate the reaction RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. The reaction RA is acting towards the point B in the clockwise direction. So it will be positive and the distance is 10 meter. So 10 RA. The point load is acting towards the point B in the anti-clockwise direction, so it will be negative and the distance is 5 meter, so minus 72 into 5. The moment is acting in the clockwise direction, so it will be positive. Finally, we are getting RA is equal to 15.7 kN. To find out RB1, let us apply the rule summation of vertical forces is equal to 0. We are having three vertical forces, RA and RB1 are acting upwards, so they will be positive. The point load 72 kN is acting downwards, so it will be negative. RA we have already calculated, we can apply that. After calculation, we are getting RB1 is equal to 56.3 kilonewton. Now let us take the span BC and find out the reactions. In the span BC, we are having an anticlockwise movement MBC which is equal to 203. In this span, first I am going to calculate RB2. For that I am going to take movement about C. In this case also, I am moving towards right hand side. Clockwise will be positive, anti-clockwise will be negative. RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 8 meter, so 8 RB2. The UDL is acting towards the point C in the anti-clockwise direction, so it will be negative and the distance is 8 meter. When the UDL comes, we have to multiply with the distance and the distance by 2, so 8 by 2. The movement is acting in the anti-clockwise direction, so it will be negative. Finally, we are getting RB2 is equal to 169.375 kilonewton. Now let us apply the rule summation of vertical forces is equal to 0. Here we are having three vertical forces, RB2 and RC are acting upwards, so they will be positive. The UDL is acting downwards, so it will be negative. When the UDL comes, we have to multiply with the distance to get the total load. Finally, we are getting RC. We have calculated the reaction in the point B 2 times, so let us add them. Finally, we are getting RB. Now we are going to draw the shear force diagram. Before drawing shear force diagram, let us calculate the shear force values. I am calculating the shear force values from the point A to the point C. In this case, I am moving towards right hand side. The upward forces will be positive. The downward forces will be negative. You can see the calculations here. For the point loads, we have to calculate the shear force at just left of the point and just right of the point. Now you can see the shear force diagram. If there is UDL, the shear force line will be inclined. You can see that in the span BC we are having UDL, that is why we are getting inclined line. For the point loads, it will be a straight line. In the shear force diagram, if we are getting negative values, we have to draw below this line. If you are getting positive values, we have to draw above the line and then mark positive and negative. Now let us make the bending moment diagram. For that, first we have to make the free moment diagram, then end moment diagram. After, we have to combine both of them to get the bending moment diagram. For making the free moment diagram, we have to consider each span as a separate simply supported beam and then draw the bending moment diagrams. In a simply supported beam, if the point load is acting on the center, the formula for maximum bending moment on the center is WL upon 4. Here W is 72, L is 10. We can apply in the formula, finally getting 180 kilonewton meter. In the simply supported beam, if the UDL is acting for the full span, the formula for bending moment is WL square upon 8. Here W is 36, L is 8. We can apply in the formula, finally getting 288 kilonewton meter. We know that if your point load is acting in the simply supported beam, the bending moment diagram will be in the shape of a triangle. If the UDL is acting, the bending moment diagram will be in the shape of a parabola. In most of the cases, the free movement diagram will be positive. It will be rarely negative when there is coupled movement in the beam. Now let us draw the end moment diagram. We have already calculated the final moments. Using these movements, we have to draw the end moment diagram. In the point A and in the point C, the moments are 0. So the end moment diagram will be 0 in the points A and C. In the point B, we are having two moments, MBA and MBC. MBA is acting in the clockwise direction and MBC is acting in the anti-clockwise direction. For drawing the bending moment diagram, we have to see the direction of the arrows. Both of the arrows are indicating upwards. That means we have to fix this point above this line. Then we can join this point from the point A and from the point C. We already know in the point A and in the point C, the bending moment is 0. Even though we are having two movements here, we should not make 2 points. Only one point we must make because both of these arrows are indicating upwards. End moment diagram will be negative if it comes above this line. If it goes below the line, that will be positive. Right now it comes above the line, that is why it is negative. We have made the free movement diagram and end moment diagram. Now let us combine both of them and draw the bending moment diagram. After combining, wherever they are acting alone without mingling, we have to mark them. Here we are having the free movement diagram alone, so we are marking as positive. Here end moment diagram, so negative. Here free movement diagram, so positive. Then we have to mark the values also. Wherever the free movement diagram and end moment diagram are acting together, we are not marking anything, we just keep the space empty. If you are very experienced, no need to draw the free movement diagram and end moment diagram. We can directly draw the bending moment diagram. We are going to end this session. Thank you for watching this video.